All right, so in the talk then, I thought it's obviously not computational, but it's the ideas, all of which go into the computational. And so the first 2 points, so I've split it into four, so about a quarter of the talk each. The first two are, of course, favorite topics, but they are a stripped down version of what I talked about when I was at M&M. And actually, a number of the people here were also at this M&M meeting in Portland. And then the last two are both published papers, one about a year ago, one this year, that came from some work Chris Russo and I have been doing. And a lot of what I'll talk about comes from talking and doing experiments with Chris. And all of them are geared towards the idea of trying to find what are the problems with our current images and how can you get more information out of your specimen into the images. And then once you've got the images, how do you get more information out of the images into your computer, into your structure? And these are the sorts of things that we worry about or have worried about in the past and still are in some cases. So one of them is just the electron optics, but now we have these wonderful microscopes with good vacuums, good bright sources without too much energy spread. And so in a way that's solved. So one question is, can you do it cheaper? The second one, radiation damage, you can never get around it, but the consequences of radiation damage like charging, beam-induced motion and so on, you can get around. And the goal, of course, is to make it so that the actual intrinsic radiation damage is the only thing that's left that's limiting you. And of the things that it causes, one of them is this physical mechanical beam-induced motion that in Alberta's talk, that the first few frames, we now think that is the main problem, actually. And you saw in his movies, there were, for the 38 frames, the first two had dots with sometimes 1 or 2 angstroms between the first frame and the next frame. That means that during the first frame, it's moved by several angstroms. So that's blurring your first frame and so on. And then we've also worried about charge buildup during, so you put the beam on, it's an insulating specimen, the specimen charges up, and then during your exposure, that will change the defocus a little bit. We've worried about it, and I'll show some data about it. And then there are also, because it's an insulator, microscopic charge fluctuations, which in the past people described back in the 60s as the bee swarm effect. If you go far out of focus, low mag, you see the specimen twinkling. All of our specimens are twinkling, and the question is that one of the killers? And I'll say something about that. And then once I talked to Bob Glazer when we were thinking that it'd be better to have some lower voltage microscopes. And Bob said, no. He said, if anything, we want a high voltage. And then his reason was he wanted to get rid of the curvature of the Ewald sphere. But there are, in a couple of programs now, cures for that. And then the last thing I'm going to talk about is to do with elastic versus inelastic scattering. Elastic is what we want, and inelastic is associated with the radiation damage. And then obviously later on, we might get more benefit out of liquid helium. All right, so the first part of the talk then comes from work that Peter Rosenthal and I did a long time ago. And this is our overall theory. I'm not going to go into it, but the idea is this is the average structure factor, and this is the resolution or resolution squared. And these are the form factors where essentially at high resolution, all the atoms scatter randomly. At low resolution, they scatter coherently. That's what we expect to happen. The images are a bit blurry, so you lose high resolution features. The computer doesn't get the angles and positions quite right, so there's more blurring. And then there's a certain noise level, and as you put in more particles, you drop the noise level, and the idea is to get the noise level below the signal or below the signal after it's been blurred and so on. And then when the signal drops to equal the noise level, that's the resolution you're at. We're trying to make that better. So this was Peter's actual data in the year 2003 on this pyruvate dehydrogenase. It gave an 8.79 angstrom map. That was the best we could do then with these things. And of course, now it's much better. But this is the red curve is the experimental version of that theoretical hand-waving curve. And you can see they're all coherent at low resolution. You can see them. It fades down, and then it comes down, and then you have the noise level out here. And this is roughly the resolution, 8.7 angstroms. And the B factor that describes this structure factor against the square of the resolution, 1 over d squared, the B factor was 1,000. And that was the factor that was limiting us to 8.7 angstroms. So Peter came up with this plot which we've now called the Rosenthal plot, which was the resolution that you're reaching, and on the vertical scale, and this was Peter's idea originally, the log of the number of particles. And then that data set he collected, that open circle was his data, and then this was our hand-waving theory, the one that Fred referred to that we made about 1995. And then we said 10,000 particles were needed. However, we were using a very, very conservative criteria. So now actually we think 1,000 asymmetric units, so 50 icosahedral viruses ought to work. You shouldn't need these millions of particles unless you want to have, say, 100 different conformations. Anyway, Peter's conclusion was, this was the resolution we got, the 8.7 angstroms. If we wanted high resolution, which we did, one idea was you collect more particles, and then you can get to 6 angstrom resolution with many centuries of work in collecting data. So we said this is a bad idea, so we stopped that project and started to think about other things. But Peter's idea in the dotted lines was you should make the images better, computer programs better, get the B factor down. And in 2003, this is about the maximum we imagined was possible. And the idea was then if you could get it down to 125, you could go out here and you'd get 3 or 4 angstroms with less effort than we did back in the year 2003. So that is one of the things that we like, and this particular plot is a good one to judge how well you're doing. And here are 3 examples of more recent data sets. So this is, say, 2015, and you can look at, so this is the same Rosenthal plot. This was from Radostin Danev's work in Martinsried with Wolfgang Baumstein on the proteasome. And they, with a faceplate as well, but they collected a lot of data, 100,000 particles, 1.4 million, and they got about 2.2 angstrom resolution. And then they just left particles out of the data set and recalculated it. And it's a pretty nice straight line. And that tells you that one B factor more or less explains the behavior of all the data. And the B factor is 100, not 1,000. And then these are a couple more data sets that Vinoth Kumar collected in Cambridge in collaboration with two groups from India. And now Vinoth is back in Bangalore running their national facility there. But 2 or 3 years ago, they had B factors of about 100 on these. So 100 was state of the art 2 or 3 years ago. And the idea is that if you go down to what is a lower resolution, say 10 angstroms, you're only needing 800, 6 angstroms, 50. So the number comes out about this 1,000 particles. And the key is, the reason that you need more is because the B factors are not as low as you would like. And that's one of the things we like to improve. The second type of plot that we really like is exactly what Alberto was showing before, which are these plots, frame number in the data set, 2 ribosome data sets collected with different dose rates. And they were both from Shor's group, when they were wondering whether if they did more finely spaced frames in terms of the electron dose, maybe they could overcome this blurring business and maybe they wouldn't move as far. And actually the shapes of the curves were identical at that time, and they're peaking around 5, 6, 7 electrons per square angstrom, with the early frames being bad because the images are blurred in some way, and then the later frames lose information because of radiation damage. And that was then a beta-galactosidase data, probably the one that was 10017 that was talked about earlier this morning, and then mitochondrial complex 1. All of them had more or less the same shape, and we have worried about this, think it's a very important problem to solve, and it's somewhat solved, but not completely solved. But Chris Russo and I have been worrying about why it has this shape, and that was one of the questions. So we've got this one. So this is not published, and the numbers aren't exact at the moment. But the idea is to try to explain the shape of this bottom curve, which is what you get when you evaluate the quality of the data. And these were the various things that were on that first slide that we thought of that might be contributing to it. And that the idea that in general is that theoretically, you make your specimen, you do the Dubochet punch freeze, you take images. The first frame, the one that's bad at the moment, should be absolutely the best frame. And so that means it should, relative to the intrinsic structure, it should have a B factor of 0. describing the fading out of the data. And then as you expose it to more and more irradiation, 1 electron, 2, 3, 4, you'll be gradually introducing disorder. The damage to different molecules will be a bit different, and it'll fade out. And we don't know that number, but we think it's between 5 and 7, because we measured it by fading of diffraction spots in crystals, between 5 and 7, more or less independent of what you're looking at, although some proteins are slightly more sensitive than others. And then the idea is that by the time you get to 25 electrons per square angstrom at 300 keV, you've got a B factor of about 150 here. And so it's fading out, and at the moment, we don't have a graph like that because the water molecules move around and push the proteins around because there are charge fluctuations, charge buildup, and mechanical specimen motion. And what we've tried to do is investigate those to see which ones are more important. And I'm just going to show you a couple of examples now of 3 of these things. So one of them, and this is a paper that Greg McMullen and Vinoth worked out about 3 or 4 years ago. And the idea was, why do we not get beautiful tone rings when we take a picture of pure water? So the middle one is a picture of a carbon film. On the left is our typical tone rings from a defocused carbon film image. And it's a movie series, but in this picture of carbon atoms that don't move, you add up all the frames of the movie, you get a beautiful tone ring pattern. If instead of doing that, you add up the power spectra of the individual frames, it's weaker, because the atoms, when you add them up, they're adding up coherently, and these are then being added as amplitudes. And when you square it, you get a nice pattern, whereas here you're adding the power spectra and it's weaker. This is the same image that it's been calculated, the Fourier transform calculated in 2 different ways. This is the Fourier transform of the summed images. That's the sum of the Fourier transforms of the individual frames. This is weaker than that. If you do the same thing with a pure film of water, this is what you get on the left. So in other words, you add up the frames, you can see a peak around 3.7 angstroms from the water molecules. There are faint tone rings, but they're very faint. If you, instead of doing that, you add up the power spectra of the individual frames, it's much stronger. And that's because here, the carbon atoms have not moved at all. Here, all the water molecules, they're moving to a certain degree between frames. And we kind of validated that by taking that same carbon film, and now instead of taking a movie of one area where all the atoms are the same, we took 25 different areas, being careful to adjust the defocus to be the same. And so this is the picture of the same carbon film. On the left, we've added together 25 uncorrelated areas where all the atoms have moved between each frame, and then that's the power spectra. So this one looks identical to this, right-hand side, but the left-hand side is weaker than that in a similar way to what it is in the ice. And then the thing is, this is a picture of the same ice view, so you can process these frames in different ways, and that's what this bottom panel is. So this is the number of frames you average before you do the Fourier transform, before you add the power spectra together. 1 is the same as what you've got on the left. And so for this middle one with the carbon film that's not moving, the more frames you add together before you calculate the Fourier transform, the more power you get. It's a straight line like this. Whereas on the right-hand side, the more you add together, the weaker it gets. So this is atoms that 100% of them move between one frame and the next. This is none of them move. And so the ice in between, depending on the exposure rate and so on, has a different shape. And from this, you can show that the water molecules, roughly speaking, move 1 angstrom for every 1 electron per square angstrom. So by the end of it, by the end of a normal 25 electron, the water molecules have moved by 5 angstroms. That pushes the protein molecules around and causes a little bit of blurring. But by the time you're at a ribosome, they move by less than half an angstrom, so it doesn't really matter. The second one is charging. Here is an image of a wholly carbon film with a thin film of water on it. And this is low mag, high defocus, before we put the beam on it to take a high resolution picture. And we're going to put the beam on in the middle to take a high resolution image of it. And if you then go back and take a low mag afterwards, this is what you see with that type of low mag images. So in the middle, that is the 1 to 2 angstrom, 1 to 2 micron diameter beam that you'd be using in your normal high mag image that gives us all the beautiful data that we're going to be using to determine the structure. And it's gone dark. And the reason it's gone dark is it's a patch of positive charge. John Berryman was the first to observe this in 1990. We call this the Berryman effect, the dark patch, and sometimes people use that for aligning the alignment between their search and their image. What we didn't, this is work that Chris Russo and I did about a year ago now, what we didn't and had never seen before that, accompanying the dark spot, there are all these little white spots. And that's because the electrons that came out of that patch, creating positive charge, some of them have gone to the column and disappeared, but others have landed on the specimen, the bit that's not irradiated. And so these are little areas of negative charge, positive charge, and the lensing effect from having a big defocus tells you about it. From these, we can measure two things, the kinetics and the amount of charging. And the charging does perturb the image a bit, but basically most of that's happened within a fraction of an electron per square angstrom. So it's important, you can measure it, but it's not something that we worry about too much. And then the last thing is this microscopic charge fluctuation that we've worried about, and that's another paper. And this is, for those of us who are in EM, we found this really thrilling when we were doing this. So this is an image here of a thin film of ice made in exactly the normal way, and we're taking an image of it in exactly the normal way, so 20, 25 electrons per square angstrom. But instead of protein molecules, we've got 100 angstrom gold particles in it. And some of them are just little black dots. That's because the gold particles rotate, and inside the gold atoms are in a crystalline array, and only some of them are in the right orientation to look with your beam down the planes of gold atoms. And so that one there, you can see the little white dots. That's the diffraction of the electron beam off the planes of the atoms, which are obviously coming directly towards us, whereas these ones are not doing. So if you cut that out and magnify it, here it is. And if you cut out one of these diffraction fringes and magnify it, you see the fringes from the gold atoms. So you've got the two beams coming out. This is basically just Young's fringes from one reflection. And so if you then calculate the Fourier transform of those three, the whole image, this is 4,000 pixels square, and the signal is very strong. So even though you've got the noise from the whole image in the background and so on, this gold particle and its two little fringes here, you can see it in the Fourier transform. And this is a 2.3 angstrom spot. If you cut out that bit of the image and do the same thing, you get the same spot. All the other ones from these other gold particles have now disappeared. You've only got that one. And then if you magnify it more, these two spots, you can see it's got the fringes across it. These are the tone rings from the gold particle, which another way of thinking about it is it's the interference between this image, real space image, and this real space image gives you this reciprocal space modulation, the tone rings. And you can see it in the raw. That is a little bit of the Fourier transform of the whole image. You can still see them. Whereas if you cut out one of these little parts of the image and Fourier transform that, that's just, there's no long-range interference, and you get a nice non-tone ring sampled image. But what it allows you to do is to defocus by different amounts. So here is 2, 4, 6, 8 microns defocus, and here are the fringes, and you can see it's more or less the same. So whatever amount you defocus, you can still get the fringes, and that's telling you that the coherence of your source is adequate to give you that. And as you defocus, normally you have an envelope function that gets worse, and depending on the coherence of your source. But the microscopic charge fluctuation is something that is all over the specimen, and the different beams going through the different parts will be seeing different microscopic charges tilting the beam, and that we think should have an effect on the envelope function. And when you then evaluate that quantitatively by looking at the power in these spots as a function of defocus, here's the defocus, nothing to 12 microns. This is a normal picture, typical magnifications. The coherence of the source is that top line, showing you it's not bad. You've lost a bit, 20 or 30% of the power at 12 micron defocus, and the gold particles in ice rather than gold foil lose a little bit more. So there is some effect of this fact that the specimen is an insulator, and there's a twinkling and there's a bee swarm effect, but we think that it's not really something that's going to kill us. We can make up for that by 10 or 20% more images. So we come back to that thing. So we've now evaluated these things, and we now think, Water browning in motion, you can measure it. It blurs the images, it makes the protein molecules, small ones move further than big ones, but it's not a killer. You can make up for it with a little bit more images. Similarly, the charge buildup, the Berryman effect, and even the sort of the negative charges that are around it, the kinetics of that means it's basically all over in a fraction of the first frame. And then these fluctuations, again, they're important, but they're not killers. So you're left with this one thing, which is what we would like to fix, either by making the specimens so tough and strong that the particles don't move when you put the beam on them, or you treat the suspending medium somehow or other to stop them moving as much, or you get really good detectors such that you can do the deblurring from the motion correction better than we can do at the moment and get rid of them right down to a fraction of an angstrom and so on. But this big blue area then is the key problem. And of course, improvements have been made compared to those images that I showed before. And one of the papers where they've done this really nicely is Dmitry Lyumkis's work with adeno-associated virus. They went to a lot of trouble aligning the beams, small illumination, touching the hole, and they used these thick gold grids that Chris Russo developed and got a really nice map like this with better than 2 angstrom resolution and lots of nice side chains and so on. But the one reason I liked this paper, it was a year or so ago, was that they did these 2 plots that we've been studying and trying to make better for years, and they had a B factor of 60, which was, at the time they published this, was the best you could do. And the great thing was Nico had put into his program FreeAlign back in 2006 an Ewald sphere correction, and this was the first data set where switching that on gave an improvement. Prior to that, Nico always wondered maybe he'd programmed it wrong or something like that. Anyway, this is an improvement. And then also in this information versus frame number, you can see this has moved to the left of where it was before. So it's now peaking at about 3 electrons per square angstrom rather than 5, 6, or 7. Okay, so that's a nice demonstration of it. It shows we're moving in the right direction. And then another worry we had is there's a lot of evidence now. So this is bad, and then it's still fairly flat. But could it be that beam-induced damage, perhaps there's a sort of beginning area where there isn't any damage, and then it takes off, rather than the curve we thought, which would keep going up and up like this. And for this, there's a really interesting paper from the X-ray community. This is Bob Thorne from Cornell, and this is X-ray data, looking at intensities only, none of this beam-induced motion, but they're looking at B factors. And here is their dose in terms of radiation damage. Here is fading of high-resolution spots, and here is their B factor increasing. And it's increasing by about 18, something like that. So if you translate what they've done into what we do, roughly speaking, this is the 3 electrons per square angstrom, and what you've got is pretty much a linear thing. So we're now sure that this potential gain from getting better motion correction, either in the specimen or in the computer, is going to produce, once it's been cured, it's going to produce a big effect useful for us in the field. And then one last thing about this, these gold particle images in ice, they do exactly the same thing as the proteins. The first few frames are dreadful, and then you keep taking them and so on. So here is a complete data set on the whole of that gold sequence that I showed before. So this would be the first image at 2 microns over focus. The second one would change it by 1 micron. And this would be after 7. So this would be like 150 electrons per square angstrom, gold particles in ice. The one that's exactly in focus has cancelled out the gold fringes. So that's why there's nothing in here. But you can see the very first frame here at 0.3 electrons per square angstrom. Because the gold signal is so strong, you can see that the gold is there, and that very first frame has the image. But if you add up all these, and there's, I think, something like 60 frames or something like that, if you add them, doesn't say what the number of frames is, but if you add them all up, that image is all blurry, because during that very first exposure of the beam, it's blurry, just like we get in the structures. And then I'll finish with, and then one last thing after this. But here are 2 really nice data sets. This is Alberto's data, redone several times by Relion, and they managed to get their B factor to 56. And this one is the Wim Hagen data set that you also saw with B factors. So at the moment, we've got B factors of 50 or 60, but once everything is cured properly, you'll be down to about 30, and you'll need 5 or 10 times less data. So the last two things now, and I see my time is, one was Ewald sphere. So this is the idea. You have the specimen, you put the beam through your object, the diffracted beams come out, they get focused back, and then you can think of this as the gold, the dark particle and the two fringes. And the normal way that we correct for the defocus, CTF correction, you take these two fringes, you correct the whole image, and you put the fringes that would be defocused, you put them back into the particle, and that's the -2 sine chi of the CTF correction. But Chris and I thought, having seen these gold particles, and we hadn't realized at that stage that this is more or less what Nico had done about 15 years earlier. The idea is that you use, instead of -2 sine chi, you use e to the I chi to move that fringe back onto the particle, and then a separate one to move that fringe back onto the particle, so that you get the correction for these two diffracted beams that are coming out in opposite directions and have different Z star heights. So these are the ones that, if you have a curved Ewald sphere, these are not the same Fourier component of the same fringes. They're slightly different, and that's what gives you the benefit of doing that. So the algorithm. So we explained this to Shores and probably Takanori programmed it into the program in a slightly different way to what Nico put into Freealign. So Freealign does e to the I chi, e to the minus I chi, just like it is here. The extra wrinkle that's in Relion now is that after you've done that, you put a mask around it to get rid of the one that you don't want. So when you shift this to the left with e to the I chi, you get the correct thing for the structure, but you also get this this ghost that you don't want. So putting a mask around that allows you to get rid of some of the noise that's systematic, and it would not improve your Fourier shell between the two halves of the data, but it will improve the Fourier shell between the model your map you end up with and the model that you end up with. And they've done this and got a number of data sets to show a definite improvement. And the one that I'm going to point to is just, this is in their Relion 3.0 paper, but I'm only going to point to one panel here. And so this is an old data set, P22, viral capsid, a big thing, such that Ewald sphere would, and then this is when they do the Ewald sphere correction correctly and incorrectly, and they've got something like half an angstrom of improvement in resolution. So the conclusion is that the radiation damage you can't get rid of, but all the other things you should be able to work at to get rid of them, and we're part of the way along that track. So the last point then is this business about, and I'll just show you it. Vinoth and I wrote this review in Quarter Reviews of Biophysics about 3 or 4 years ago, when we said it's wonderful that we have these new microscopes, and they're very expensive, and we love these national centers where you go there and someone talks to you nicely, holds your hand, collects data for you, and so on. And we like that. However, many projects, particularly if you're trying to fix this business of beam-induced motion, you need to get on the microscope every day. And in our lab, you have to book, and it takes like 5 weeks before you get your day. And then you've done something wrong, and you need another day. So what we need is daily access, and we said we want a cheap microscope. And then we thought, since none of the manufacturers seem to be making any effort in this direction, we better check a few things and see whether or not that was a good idea. But anyway, the general idea is we need a cheap microscope, 100 or 120 kV. And when we wrote this, we were just looking for a cheap one. But it turns out, in the old literature 50 years ago, it's known, and this is from the Bloch and Bette's work about elastic and inelastic cross-sections. And this is a paper that's just been published, or later on you'll see it. Matthew Peat, who gave a talk about it, probably today in M&M. The idea is that here is a plot of the inelastic cross-section for electrons scattering off atoms, and here's the elastic scattering cross-section, and here's the energy of the electrons from 1 keV to 100 MeV. The elastic comes down, and when the electrons are relativistic, it goes straight. The inelastic ones comes down as a minimum ionizable particle, and then as the electrons get heavier and relativistic, and there are other effects, Cherenkov and so on, it goes up here. And so there's a minimum point, and if you take the ratio of these two, the elastic is what we want, the inelastic is proportional to radiation damage, and then there's obviously, if it's 1 keV, the electrons won't even go through our specimens, so you lose them all. So we've got this formula, transmission times sigma E over sigma I, and that's this dotted line. And when we plotted it in about a year or so ago, the peak of it, which tells you how much information you get for the same amount of radiation damage, came out at 100 keV, not at 300 keV. So we thought we'd better check this, and I say I'm at 0, but here is elastic cross-section of a thin film of graphene as a function of the energy. It has a straight line. The slope of that is exactly in agreement with that theory, and if we do the 100 keV to 300 keV, we've got a cross-section of 2. If you do the same thing for inelastic, the ratio is 1.6, so you've got something like 25–30% improvement. The inelastic is inelastic, but it's proportional to radiation damage. So here is purple membrane spots fading. Here is 100 keV critical dose, 300 keV. The ratio comes out about the same. So that's telling you that even though the inelastic events may not all be doing damage, the damage is in proportion to that. So you come back and then you get this same curve again. The full curves now have been checked by experiment against these theories, and the theories are exactly correct. So if you've got a 300 angstrom thick specimen, which would include ribosomes, 240 angstroms, so anything less than 5 megadaltons would be in this or even thinner, and the optimum energy is 100 keV. If it's thicker, like let's say adenovirus or rotavirus, you might want it to be a bit thicker, but the gain that you get isn't all that big actually. So we think 100 keV would be really good for many things. So the final conclusion then is that looking towards how we're going to improve it, obviously better detectors at all voltages would be good, 100% DQE at low spatial frequency, and then really as high as possible so that you can do this super resolution thing. But if you process images, electron events on the Falcon at the moment, you can get above 50%. It's not in the commercial version, but it is possible. And then this beam-induced motion, probably if that could be fixed, you'd get your overall B factor. It won't be ever 0 because you still need to record an image and there will be damage down to maybe 30, and then you'll get either less images will be needed, or you'll get more substates or whatever. And then these are two things that we've been thinking about for the future. What will a CC corrector do to help us with tomography, and will liquid helium help? And then I'm just going to finish with the, so this is, so in the 4 bits of the talk, the earlier one was essentially all of the things that Peter Rosenthal and I used to worry about that provided with a framework for thinking about it. We were involved with detector development, 2 people, Wazi and Greg at LMB, and then 2 people at Rutherford Appleton, and they're still involved with sort of next generation detectors. And then most of the thing that I talked about came from discussions Chris Russo and I used to have, but eventually turned into experiments with Matthew Peat, his postdoc, and Katrina Nadanova about all these different things that are worrying for us, but may not be rate limiting in the way that radiation damage is. So hopefully that's a little bit of a sort of a flying tour of all the things we're thinking are important. Thank you very much. Yeah.